Hello, and welcome to the 17th lecture in the Jabrah Reinforcement Learning Series. So today we're going to be talking about maximization bias and double learning. So just to give a brief overview of what we're going to go through this lecture, we're just going to be continuing from where we left off in the previous lecture when we started talking about SARSA, expected SARSA, and Q learning. And we're going to identify one problem with this algorithm that is known as maximization bias, and like how we actually overcome that problem by utilizing this technique known as double learning. So just to say this beforehand, this will mostly be a programming lecture. We're going to go through a basic implementation of the Q-learning algorithm, and we're gonna show what this maximization bias actually is, and we will implement the double Q-learning algorithm as a measure to actually minimize this bias and show why we might actually want to use the double Q-learning in actual real cases that we have to deal with due to the convergence properties. But having said that, I should briefly mention that, well, let me just go back to what we looked at last time. So the techniques I'm discussing here are applicable to all the algorithms I covered last time, but here our focus would just be on the Q-learning algorithm. But you can just apply the same, logic to the other algorithms with minimal effort, so should be fine. So what if you remember from the last lecture, we said that when we're doing the Q-learning algorithm, we had a couple of steps we're following. One, we were initializing our Q values. So I'm just going to brush through the steps in the algorithm here, but if you want more details on the actual flow of it, please look at the previous lecture. So we said we initialize our QSA to 0. And then we generate an episode. After generating an episode, we take the state, like our initial state. From our initial state, we take an action. And the action, how do we determine it? We use an epsilon greedy approach. But basically what we end up doing is just taking an argmax over all actions of QS, A. Right? This is what we end up doing. With some probability we'll take this, with some probability we won't, and so on. But I'm not gonna go into the details here because I already covered them last time. And then final step was basically to update our QS, A, and we were basically doing it using the following formula. QS, A is so plus alpha times r plus, so it was gamma, I guess, maximum over all actions of Q. Let me write it like this: QS prime, A minus QS, A. Yeah, this should have been the update rule for the Q-learning algorithm, but our focus here should be on one item mostly. So let me go through that. So we have this argmax operation and we have this maximum operation, right? So what's happening here, and I'll discuss this problem later on after we actually implement the algorithm, is that, well, we are taking the maximum over these Q values, but initially these Q values are equal to 0. By the way, we're doing step 1, 2, 3 all iteratively, just in case oh yeah, anyway. So, but the whole point is that we're taking a maximum over all Q values, and initially we don't know what they are. So there's already a bias involved in this operator itself. Um, because we're gonna use the same Q function to determine what the best action is using an epsilon greedy approach. So that's where this whole maximization bias comes from. I'm going to detail it more later on, but I just wanted to introduce it before I actually start implementing things. So the thing is that it's not just this algorithm. Like all the control algorithms that we have discussed so far have this maximization operator that we're dealing with. And in Q-learning, the target policy is the greedy policy given the current action values, right? So again, this is defined by a maximum operation, and this leads to a bias. So let's actually go through the example we're going to be coding today, and it's actually a simple one. You will realize. So let me open my book. Okay. So this is the problem that we're going to be tackling here. So first, let's say we are. So let me just write. This will be our programming problem, I guess. So basically what we're going to do is we're going to have the following environment. We're going to start from state A, right? So this is where we start. And so this is our start state. And from this state, we have two actions that we can take. So either we take the action to move to the right, and we get a reward of 0, and we end up in a terminal state, right? Or we take an action to move left, we get another reward. We get a reward of 0 from here, and we end up in a new state that we term as B, right? So this is the nature of our problem. And then from B, let's say we have about 10 actions. So we can take up to 10 actions, action 0, action 1, and so on up to action, well, let me just say action 1, 2, until 10. So we can take a number of actions from B, and we end up in a terminal state here. And the reward that we get from B, so the reward here, it follows a normal distribution with mean of minus 0.1 and standard deviation of 1. So maybe I should use a different color here for the rewards, just to make things clearer. So this is a reward of 0, here with 0, and here we're following a normal distribution, right, with the mean minus 0.1 and standard deviation 1. Okay, so this is our problem, right? So we start from A, two actions are available. Move right. If we move right, reward is 0, terminal state. Move left, reward is 0, we end up in B. From B, 10 actions are available. The reward that we get from B is just follows a normal distribution with a mean of minus 0.1 and standard deviation of 1, or variance of 1, and so on. So just before even solving the problem, we already know what the best action to take in the state is. Like if we're starting from A, the best action to take is the right action. It makes more sense to take the right action in this case, because if we take the right action, our total reward, right? So if we take the right action here, our total reward will be 0, right? This will be what our reward is. But if we take the left action, on average we're gonna get a reward of minus 0.1. That's essentially what this is. So on average we'd get a reward of minus 0.1. So that means that the algorithm that we make should learn to take the right action if it's starting from state A. That's essentially what it should do. So the problem itself is a very simple problem, but the things we're going to learn from it are actually quite invaluable here. So having said that, let me actually open up our coding platform here. So let's see if I should wait. Okay, maybe we can zoom in a bit. Okay, so that should be better. Don't know why I put this here, but yeah. Okay, so what we have is, first of all, I already coded up the environment here. So I'm gonna just go through the code of the actual environment, and what we are going to do is we're going to code up the main.py. We're gonna look at the QLearning part, which is what you call this, the QLearning file, and we're gonna go through the double QLearning file, and we're gonna go through the environment, the main file where we will put get everything together, so to speak. So first, let me delete this. Okay. So let's start with the problem itself. We're going to solve the problem I introduced here using QLearning. Essentially, that's all we're doing. So I'll discuss the environment first. So in the environment, we have our start state. We're going to start in state A, and our terminal state is T. So let me actually label these things here. So we're gonna, this is A, this is B, this is our terminal state, which I'll label as T for terminal, and this is also T for terminal. That's what the states are that are available. And from B, we have around 10 actions that we can take. Here we can take action 1 to up to 10. And finally from, let's see, so the possible actions, if we're in A, we can move either left or right. If we're in B, we can move like, we can take any of these 10 actions. Here I'm just using both strings and int, but you can just ignore that. Just think of it conceptually in this case. We can take any of the 10 actions. And if we're in the terminal state, we cannot take any actions, right? So that's what these possible actions are. So we've covered it up to that. And then the state transitions, essentially they're saying if we are in state A and we take the left action, we'll end up in B. If we're in state A and take the right action, we'll end up in a terminal state. If we're in state B and we take any action, any of the 10 actions here, we'll end up in the terminal state. So this is just what the state transitions is actually showing in this code. And we look at the reward. The reward is truly only defined when we're in state B and we take any action. So if state is B, we're going to return a reward that follows a distribution mu and sigma of minus 0.1 and 1. So we're gonna return a random.normal. So we're following a normal distribution with mu, sigma, and so on. So that's the idea here. And if in any other place the reward is 0, as we saw from the example. And the step function says we start in some state, we get a reward, we move on to the next state, and we get a done. So what this is doing is you provide current state and action, And based on what we discussed here, this will give you the reward in the next state and whether you're done or not. That's what the step function is doing. So this is just following the same pattern that we had before. So this is what our environment is, and we've defined everything that's here. We've defined everything here in this environment. So the next step now is to implement our Q-learning algorithm, right? So let's actually start with that, with our Q-learning algorithm. So there are a couple of things we need to define, because we are going to be doing what do you call this? When we're actually writing our Q-learning algorithm, there are particular number of things we need to look at. So the first thing we need to define is our epsilon. So epsilon is about the exploration versus exploitation. So it's basically telling us what is the probability of us taking our intended action and the probability of us taking an alternative action. And I'll discuss it before. So we set this value to 0.1. That's what our epsilon is. And we're going to set our alpha. So alpha is coming from the alpha from the Q-learning formula. So we're going to set this to 0.1 as well. And then self dot, the next thing we need to set is our gamma. And we can set this one to say, yeah, we just set it to 1. So this will be our gamma here. Is there anything we need else? Number of episodes, of course. We need to set that. Number of episodes is equal to 300. And well, when we initiate this, we're going to receive, we need to receive our environment object here so that we know what's actually happening here. So I'm going to include here in the init our environment, and I'm just gonna set it here so that we can use it later. Self.environment is environment, and the next thing we need to state is our start state. We need to set our initial Q values. So our start state, I'm just gonna call it self.init state. I guess I'm just repeating something we already have here. This should be environment.startState, I guess, because that's what it's called here, right? Yes, we have our self.state start state as environment.startState. That's what we got here. Okay. And the next thing we need to define is our Q values. So self.Q of SA, so self.Q of S, A. So we're gonna set it to 0, right? Initially we're gonna set it to 0 for x in. So what was the name of our state transitions, right? So for x in environment dot state transitions, right? So just to show you what this would look like, I'm gonna just call the function here, just to say Q-learning agent is equals to Q-learning agent, and we're gonna supply the environment. So let me write it down here. Environment is equals to environment, and okay, we're gonna call this, right? This is our Q-learning function. Let me just print this just to make sure everything is set up properly. So here we're gonna call the main.py function. Am I in the right folder? No, cd double Q-learning. No, should be fine. Right, so we initiated A and left is 0, A and right is 0, and B and all the other actions, action 1, 2, 3, 4 up to 10, or whatever, initiated to 0. This is 9, 10, or whatever. You get the idea. So essentially, this is what we have now. So the next step we need to take, right? We've initiated all this values. So the first thing we need to define now is, well, we need to define how we generate an episode. But first, we need to define our soft policy. So if you remember from here, the first thing we have to do, so I don't have the pseudocode with me for the Q-learning, but we can infer it from here. So the first thing is we need to define a soft policy that is as follows. So we need to define the following soft policy, whereby, so with a probability, so A star is equals to, we say the argmax over all actions, right, of Q S comma A, right? So we mentioned before that this is the optimal action, and we will take this action with a probability of 1 minus epsilon plus epsilon over cardinality of AS, like the number of actions that are available. So this is how we had defined the probability of taking the optimal action, right here. And we say the probability of taking, so this is our, what you call this? This is our greedy action. And our more, say, explorative actions, we take this with the probability of epsilon over this. So we had introduced this idea of exploration versus exploitation when we started talking about off-policy Monte Carlo, but essentially this is what it's saying. We will take the greedy action with this probability and the more explorative ones with that probability. So what this means in our case, since epsilon is equals to 0.1, and here I'm just looking in the state where we have only 2 actions available. So we can say that the probability of taking the greedy action then will be 1 minus 0.1 plus 0.1 over 2, right? Which is 0.95. And the probability of taking the other explorative actions will be 0.05. So these are our numbers here. As this will become important later on when we're doing the plotting, but I just wanted to illustrate this point here first before we actually go about coding it. So we're gonna code our policy. So the policy will depend on the Q values. So we're gonna say, we're gonna code our soft policy, self and state. So first of all, we need to define what are the possible actions that we can take from this state, because from any state we need to look at all possible actions for us to compute this whole idea here, or even to compute this argmax of all Q values. We need to look at all possible actions that are available from that state. So what are the possible actions here? So possible actions is equals to, well, we're going to ask our environment what the possible actions are. Because in our environment here, we have the possible actions defined here. Like in A, these are the possible actions. In B, these are the possible actions in the terminal state. So that's our current situation at the moment. And as we go through that, we're going to need to extrapolate this a bit further. Since possible actions can have, well, there can be 2, there can be 10, there can be nothing. So what we're going to do is, if there's only like one action that we can take, essentially, um, then we should just take that action, uh, in that sense. But what I'm gonna do here is, right, so if maybe I don't need to write this. So first let's look at the probability of the explorative action. Let me write that first. Probability of the explorative action, and we said that self dot epsilon divided by the number of actions that are available, which is the length of possible actions. This is the probability of taking the explorative action, and the probability of taking the greedy action just to follow the same convention we had, it's 1 minus self dot epsilon plus the probability of the explorative action. So this, what you see here, is essentially what we have here. So again, this is just building from where we left off, from the lectures from off policy Monte Carlo as well, when we discussed why we're doing things this way. So if this is confusing you, please, you just have to take you just have to look at a few lectures back and you'll understand what's happening here. Okay, so the next thing we need to do here, so we have our probability of taking a greedy action, so we need to define what our Q values are. Right, so our Q values, I'm just gonna start as an empty list here, and we need to say we need the corresponding actions for those Q values, of course. I'm just gonna put an empty list here. So I'm not really writing quality code or anything here. I'm just trying to get the algorithm to work. You probably have to put more effort into optimizing the code and such, but I'm not gonna do that here. Okay, so for action and possible actions, what are we gonna do? So if state action, right, so if it's in self.qsa, so we need to check if the state and action pair are available here, because if the combination itself is not available, then something would be wrong. So we check if the state and the action are in our self.q values here. If it's there, then q values dot append self.qsa state and action, and corresponding actions dot append action. So that's what we have here. So we're going to check if all q values are the same. So check if all q values are the same, and if so, we're going to take a random action. So this is just in the case that, well, like the beginning, all q values for a state action pair are going to be the same. So ideally we want to take the maximum of the q values, as we stated here, like the argmax of the q values, but if they're the same, we want to choose them randomly. So how do we check if all q values are the same? We just check if all, right, x equal to q values so here I should put 0, right? Because Q values, we are appending self QSA state comma A. For X in Q values, right? So this is what we do. So if all the Q values are actually the same here, because in this instance, again, we are appending QSA of state and action pair. Is this okay? The way I wrote it here, I should probably put brackets here. Oh, I'm gonna have some key error, I'm guessing. Let me check if the rest of the code is fine, just quickly. Yeah, it looks fine. Let's check later if there's any errors. So where were we? Right, if x equal to q values for x and q values, then we're going to return random dot choice, right, from the possible actions. Right, so I'm just looking at the x and the q values. For instance, if it's all zeros, here I'm just taking the first value and checking if x is equal to all those values. Then just return a random action. So our greedy action would be the corresponding actions of np.agmax, right, q values. So you might be wondering where we are right now. So once more, I'm on step 2 here. So we are taking the agmax of the q values. So like I mentioned before, we will choose the agmax with this probability, or we'll take the explorative action with this probability. Here I'm just computing, like I'm just trying to figure out which is the agmax of the action, which is what I have here when I use the np.agmax of the q values from the corresponding actions. This will give me the greedy action in this instance, and the non-greedy actions would be, so I'm just gonna say wait, if I take the set of the possible actions minus the set, because I need to remove here the greedy action. This is probably not the most optimal way of doing this, but in any case, let me convert this to a list. So here I'm determining what's the greedy action and what are the non-greedy actions. In our case, it's not a problem essentially, because we only have 2 actions to take, left or right. And one of them will be taken with this probability, which is 0.95. The other one will be taken with this probability, 0.05. Probably when we're here, things will change a bit, but we don't really care about this for our purpose. Okay. So where was I? So this is the non-greedy actions. So which action should we take? Now we need to reflect the probabilities that we saw before. So here I'm just gonna use the random.choice again. So yeah, I used np.random.choice. Let me use the numpy version because it allows you to put probabilities. So we're gonna do it for the greedy action plus the non-greedy actions. Now that I think about it, it might be easier to just generate a random number and see if it's less than or greater than or 0.05 or 0.95 and so on. But whatever, I'll just keep it like this. So the probability, so when you use numpy.random.choice, it allows you to specify the probability. So I'm gonna say the probability is the probability of taking the greedy action, right? Plus, which is, this is, here we've got 0.95. But in case we have more than one action, like we do in state B, I should also reflect that. So I should say probability of explorative action, right, for I in range the length of non-greedy actions. So if we have one action, this probability is going to be 0.95 and 0.05. But if we have more than one action, then it's going to be reflected. The probabilities will be reflected appropriately as well. So this is just it. One other approach you can just do is just say, well, generate a number between 0 and 1. And if it's less than 0.05, for instance, or if it's 0.95, then what you do is you take the greedy action, and if it's less than that, you take the non-greedy action, and so on. So we're going to return our action here. So that's the soft policy. So this is the part of the Q-learning algorithm that says you choose Q by following a soft policy. That's what this is doing. So let's see here. Let me test this already. If I call Q-learning agent dot soft policy from state, say A, I guess, will it give us something? So Q-learning agent has no attribute possible actions. Where is the problem here? Possible actions. I see. This is self.environment.possible actions. So we should be fine now, right? No. What's the problem here? Then random.choice. Okay, let's see what's happening here. We have a key error for 2. Okay, so Q-learning agent dot soft policy A returns sequence I. Let me check again. So here we have random.choice from the possible actions in the environment, right? And wait, line 291. In what? Okay, let me print possible actions here just to make sure. A left, right. I see. So this should be the possible actions from a given state, not just possible actions. And okay, should be fine now. So if I print here out, you should give me the best action to take. What's the best action to take? Yeah, it's left, right? Of course, it's not going to be optimized in this case because, again, we didn't actually write the Q-learning algorithm yet. We just wrote the soft policy, which depends on the QSA, but we don't know what QSA is yet. So that's fine. Let's move on. So the next thing we need to do, yeah, probably would need to check this part of the code as well to make sure it's fine, but this, yeah, because we only tested up to this part, but it's fine. We'll deal with the errors as they come. So the next thing we need to do is to define how to generate an episode. So we need to generate an episode because that's part of the Q-learning algorithm. Again, you probably, if you forgot what the algorithm looked like, just look at the last lecture, and the code was pretty simple, or in its pseudo format at least. So, but this is pretty simple as well, so I shouldn't have too many problems. So the episode, we start with an empty list. So what we're going to do here is our initial state, right? Self.init state. This is our initial state, and while true, right? While true, we're gonna start generating our episode. So we're gonna say action is equal to self dot, we're gonna call the soft policy that we defined here on our state. That's how we generate our action. And the next thing we need to do is we need to define what our reward next state and done is, I guess. This was from here. We need to define our reward and next state and so on. So we have our state, we have our action. Again, this action, I'm just gonna comment it here, is following an epsilon greedy approach here. So with a 95% probability, this function will choose the optimal action, and with the 5% probability, it will choose. With 95%, it will choose the greedy action, and with 5%, it will choose like another action, just to keep up the whole exploration versus exploitation thing going. So the reward next state and whether we're done should be equal to self dot environment dot step state and action. And one thing you'll realize is I'm really trying to separate the what's happening in the environment and what's happening with our agent, because, well, typically the agent and the environment should be completely disconnected. The agent should only go as far as manipulating the things it can, which in this case are its actions, and everything else it should really not have access to until the environment actually gives its feedback on its actual action. So we're going to append to our episode. So episode.append state. Wait, this should be a tuple. If we append state, action, reward, and next state. Essentially, that's what we want to append. And then we're going to set our state to be equal to the next state, right? And we're gonna go on and on and on, and if we're done, we're going to break. So this part should be pretty straightforward, and we return our episode. That's essentially it. So having done that, okay, let's see where we are now. Let me try to generate an episode. Qlearning dot generate episode. Okay, here is an episode for us. We start at state A, we take the left action, we get a reward of 0, we end up in state B, we're in state B, we take the action 2. Again, we have actions from 0 to 9, or 1 to 10, sorry. We take action 2 and we get this reward, and we end up in a terminal state. The episode ends. We take another approach. If we take action, we're in A, we take right, we get a reward of 0 and end up in the terminal state. So this is just following this example we had. Either we follow this path or we follow that path, and it's just reflecting what we have here. So our focus again is just on this thing here. Okay, let's move on. The next thing we need to do is we need to update the policy. Okay, so first things first, actually, I'm going to go through something. Like, I'm gonna start an initial plot here just to get things moving. But one question we need to ask ourselves, actually, before even getting started, is what is actually the optimal number of times that we should take the left action and the optimal number of times that we should take the right action? So if our algorithm learns properly, given the conditions that we set for it, we say that with a 95% probability, it should take the optimal action, right? The optimal action is the right action, right? So this is the right action. And with a 5% probability, it will take another action. In this case, it's the left action. We only have 2 actions here. So the optimal algorithm, after doing the whole Q-learning process, it should take, so what we want, the optimal algorithm, which is what we are working towards right now, it should take the right action. It should move right 95% of the time, and it should move left only around 5% of the time, right? Why? Because, I mean, we're not, like, we have our whole, this is what we set, actually, when we introduce this whole problem. When we say the probability of taking a greedy action is 95%, the probability of taking a non-greedy action is 5%. So these are the results that we would like to see our algorithm achieve. So by implementing the Q-learning algorithm, I am going to iterate it. I'm going to average multiple Q-learning algorithms, like among the episodes, and I'm going to look at I'm going to look at how often our algorithm is taking the left action. If it's closer to 5%, it means it's doing well. If it's higher than that, that means it's not really doing well. So this will be a measure of how well our algorithm is performing. And how many episodes does it take for it before it reaches its optimal point? These are the things we'll be analyzing here. So we're analyzing 2 things. So number 1, we're looking at how many episodes it takes to reach an optimal point. In our case, right? And actually this is our second step, and our first step is how often are we taking the left action, right? So how often are we taking the left action? That's the question we want. So let's actually set up what we want this to look like, our parameters themselves. So for that, I'm just going to say, well, let me actually start a plot. So I'm gonna say figure and x is equal to, so we're gonna use matplotlib here, plt dot subplot, plots multiply here. Okay, so we're going to, actually it might make more sense to do this. Okay, let me do this after implementing the algorithm itself. That might be more productive in our case. So because we're almost done with it anyway, so yeah. So let me just comment this out for now. Okay, where were we? Q-learning, there you are. Okay, so the next thing we need to do is to define our update policy. So I'm writing this function in this way, but please remember this function is just going to return how often we're actually taking the optimal, we're taking the left action. That's essentially what we're looking at here. And in between there, we're gonna just be implementing our Q-learning algorithm. So let me say left actions count, how often we're taking the left actions. I'm going to put an empty list here and say right actions count, and I'm going to put another empty list here, and okay, so we're gonna say for I in range self dot number of episodes. What are we going to do here? So again, left is 0, right is 0, the number of times we're taking left, number of times taking right. But yeah, you can, again, this is not optimal code, so first thing first, we need to generate an episode using the policy defined above. So we need to generate an episode, and the episode will take the format for, so let's say state action reward, and so that SAR, and next state, which we'll call S prime, SP, in episode, right? So the episode itself is the same thing that we defined before, self dot generate episode. So we're going to use a soft policy as our behavior policy. So we're gonna use soft policy as our behavior policy. In this case, we're using the epsilon greedy approach. So what do we do here? So our action is equal to A. So we're gonna be making use of this action. What do I need to define it here? Well, so we need to count how many times we're taking the left action from the start state and how many times we're taking the right action from the start state. And to do that, we can just say if S is the initial state, or should I say if S comma A, yeah, it makes more sense to do it this way. So if I say if S comma A equal. I don't know why I'm putting this here. I don't need this actually. So if s comma a equal to say self dot init state comma say the left action, then we're going to increment the count of left actions. And if, by the way, what I'm doing right now is not really to do with the algorithm itself. These are just functions to help me count how many times I'm taking the left action and so on, and how many times I'm taking the right action from the init state. Because this is essentially what we want to compute, right? Init state comma right action, then right count should be incremented by 1. So the next thing we need to do here is now let's actually go to the algorithm. So you don't need to focus on this part of the code. Well, you can. It will be helpful to follow through, but here we're looking at the possible actions, or rather I should say the possible future actions, right? So where are we right now? Right now we are here. Now we're computing this. We're now computing q s prime comma a, right? But for that, because we need to take the maximum over all actions of q s prime comma a in this formula, but for us to be able to do that, we need to first, well, compute the state, the actions that are available there. So possible future actions is equals to self dot environment dot possible actions for s prime, right? Okay, and what are our q values here? So our q values, now I'm trying to compute the q values here, and then I'm going to take the maximum of this q values. So here I need to take the maximum. So first compute this term, then take the maximum. So that's where I am in the code. So we're going to say self.qsa, right, of s prime comma a for a in, so let me try to write this with an underscore so that it's not the same as that. Probably should use better variable naming, but as long as you can follow, it should be fine. If so basically what we're doing for q values, we're just taking the q values using our policy here, the q values we defined here, and we're just saying the q values are, well, we're going to look at s prime comma a for a in all possible future actions if s prime comma a is actually in self.qsa. Again, this is just a check to make sure that our actions are valid and are defined in self.qsa. Otherwise, we shouldn't be bothering ourselves with those. Okay, so that's done. Now the maximum q value here. So the maximum q value would be maximum of all q values if the length of q values is greater than 0. Otherwise, it's just 0. So if we have nothing here, that means there are no possible future actions. When are there no possible future actions? If we're in a terminal state. So if we're in a terminal state, our maximum Q value would just be 0. Otherwise, it's the actual maximum of these Q values. So by doing this, we've implemented this section here, right? We've computed this term. So since we've computed this term, the next thing we need to do is we need to update our Q function using a different target policy. So yeah, this as I go on, I'm realizing this lecture is going to be quite long, but it's a very important one in any case. So for that reason, I have to just finish this over so that we can start on a new topic next time. Okay, so let's actually update our Q function. So to do that, we have got self.qsa. For s comma a is equal to self.qsa for s comma a. By the way, just so that you follow, I'm just now writing the entire formula here. Since we have this, we have alpha, we have r, we have gamma, we have this term, we just computed it, and we already have this term. So now it's just about putting everything together. So that's this qs comma a plus self dot alpha self dot alpha, right? Sorry, so I should put this here. Might be better for us if I do it like this, times r, the reward we get, plus self dot gamma, right, times the maximum Q value minus so wait, where am I here? So self dot qsa s comma a. So let me just make sure everything is fine. So that's self.alpha times the reward plus the gamma, which is just 1 year, so you don't really need to put it there, but just for completeness, times the maximum Q value minus self QSA of S comma actions. Okay, that should finish that part up. And then left actions count dot append left, right actions count dot append right, and let's see what I can do here. Let's say left actions count is equals to, let me convert this to a numpy array first. They're easier to work with. Yeah, I probably can eliminate most of this code, but not optimal, but we continue. Right, so here I'm doing this for one iteration. Let me actually do this whole process for multiple iterations. So I'm gonna extend my code here. Oh. What's happening? Okay. This should move. Let's move this as well. Okay. So if I define number of iterations here that we want to run our like update policy or whatever, so it goes to one. Let's do 100 or 1000 maybe. Yeah, let's start with 100. And then we're gonna have, say, a final left array. Again, you don't have to worry about what I'm doing here. It's just I'm just trying to average. I'm just trying to run our update policy multiple times so that we can average multiple runs and get a better approximation. Number of iterations. Okay, so this should be fine. And so finally we're gonna say once we're here, so left array dot append left actions count. Can probably okay. I'm gonna append the right actions count here. Okay, so let me convert this final array to an NP array again. It would have been better if I was just using NumPy arrays from the get-go, but whatever. I'm just writing, this is quite dirty code, but I'm just trying to get this done. So yeah, that's it. So now if we want to compute how many times we're taking the left action, we're just going to say it's the final left array, the number of times we took the left actions. Let me sum it on the axis 0. And probably you'll have to go into the code yourself as well if you want to follow through. Like, you can pause the video at different steps and try to print things out, but because I'm trying to keep this shorter than it's supposed to, so we're going to divide by this and plus final right array dot sum x is equals to 0, and we want it as a percentage, so I'm going to multiply it by 100 and say return out. But one other thing is, every single time we do a new run, I need to reset our policy. So I need a function that's going to help us reset our policy. So let me write that down as well. And so define reset policy. And so basically what this does is it takes QSA and well, essentially we're gonna do this part again. That should be effective enough for resetting our policy. We just okay, so here solve that reset policy. Is that fine? That should be fine. Okay, so let's see if we can get the number of times we're actually doing this. Clear learning agent dot up policy. So say left action count. So let's print and see what this looks like. Okay, already have a problem here. Yeah, probably should have tested as I went through, but I was just going through that. Probably this is not a function, so I should not be calling this. This is a dictionary. There we go. Is there anywhere else that yikes, again this is a tuple, so I should be careful here. Okay, what? Okay, something is wrong. I should not be getting a final value here. So where did I go wrong? Okay, let me print this. Let's print final right array, for instance. What does it look like? I see. That's not how you're supposed to look like, Mr. Array. Okay. So we have left actions count here. Okay, right actions count. I'd rather this be the first thing I do before doing anything else. Not that it will change anything, but okay, so what do we have here? I see. So that's how it is. Wait, let's see. So left action counts, we are appending our left action and right action, and then left actions count. This looks fine. So let me print this part. Okay, yes, we get the point. Okay, so what seems to be the problem here? Final left array. So silly. Okay. I'm not printing anything, am I? Okay, looks more plausible, I guess. So this is left. Okay, so now let's do some plotting, just to make sure that things are the way that they're supposed to be. Okay, so this isn't left actions count, but left actions ratio. Okay. So first we're going to plot this. So left actions ratio, let me just call this agent 1. range length of left actions ratio agent 1. We're gonna plot you, and we're gonna put left actions ratio agent 1. We're gonna choose the color to be red, should be fine, and the label will be Q learning. So this is our Q learning agent, and at the same time I would like to plot again range length of left actions ratio. So our optimal would be 5%. So the optimal number of times we're taking the left actions. So I'm just gonna plot this one as well, and let me make it a dashed plot. Okay, and let's make it black. And our label here should be optimal. This will be our optimal point. So this should be x dot plot. Okay. So x label. X label should be number of episodes, and x dot y label. Oh, not get set y label. So our y label should be percentage of left actions from state A. And the final and our final step would be to maybe set our legend and put it in the best location, should be fine, and plt.show, and let's see what this looks like if it's done correctly. Oh, there we go. So let me run it for a bit more iterations to average things out to be a bit better. Where is it? Number of iterations. Where are we controlling this? Do I need to organize my code better? So okay, let's run it for 1,000 iterations and see what it looks like. So this might take a minute. So one thing we already noticed here, exactly, it's right here, and this is our optimal level of 5%. This is our Q learning algorithm, and this is the percentage of times it's taken the left action. So in the beginning, this algorithm actually starts by taking the left action more often than not, because of this maximization bias that I was talking about. This is the effect of the maximization bias. But later on, as it continues learning, it reaches a point where it starts taking the correct action like more often. So around 10% of the times, if we look from this plot up to the 300th episode, the algorithm is taking the, the left action. Still, even if we're looking at this whole performance right now, it's doing this around 10% of the time, which is still less than optimal, which means this maximization bias in this simple case is already causing a lot of problems for us, right? Because our algorithm is no longer optimal. You say suboptimal in this case. So how do we go about solving this problem now? this is one effect. So one thing to learn, we've already learned from this lecture, of course, was how we implement the Q-learning algorithm itself in Python, and what the maximization bias problem actually is, and it's illustrated in this graph, and it's also illustrated here when we're saying that when we're dealing with maximum operators, this is what happens. And the final thing we learn here is how do we deal with it? That's the next step. So we identify the problem. We gave an example where this problem actually persists and actually give us suboptimal behavior. And now we need to look for a solution, right? How do we solve this issue that we're facing here? Well, in order to do that, once more, we turn to, well, what we know as double learning. So I'm going to explain what that is now. So let me try to insert a new page. Okay. So now we're talking about double Q learning, to be more specific. So this is just an extension of Q learning that helps us avoid, or rather minimize, I would say, the bias problem that we have here. And I'm gonna briefly go through the theory for this, and we're going to modify our algorithm to implement double Q learning. And after doing that, we're gonna see how it performs. So let me open up the theory page. So the first thing is, well, we're going back to the problem itself. Let me rewrite the formula again. The steps, the steps we outlined here. We said that we are taking the argmax over all actions. So this is an estimate of the maximum, right? We can call this the estimate of the maximum. But here, when we're taking the maximum of the Q values, what we're doing is taking the maximum of the estimates. So essentially, we're using the maximum of the estimate to estimate the estimate of the maximum. So already this is kind of convoluted, so to speak. And you can understand why this bias exists if using the same Q function, um, we're trying to estimate what is the maximum when we still don't know what the Q value is. And then later on, when we're trying to assign our policy, we take the maximum of those Q values that we used to update this. So this bias is actually created from this interaction that I'm speaking of here. And the whole idea behind double learning is, well, why don't we actually just spread the responsibility of estimating and choosing your policy between multiple Q functions, right? So if we spread that responsibilities, then we should have better models, so to speak of. So the idea now is quite, I mean, for me, like to understand this, it's kind of like when you're talking about an machine learning, for instance, and we do things such as cross validation and so on to just generalize better. In this instance, we're just trying also to generalize better, but in the sense that we're trying to eliminate the bias instead, I guess. But that's one way you can think of it. But in any case, let me start talking about what double Q learning actually is. So instead of having one Q function, we're gonna have two Q functions, right? So we're gonna have Q1 of A and Q2 of A. And both of these Q functions, both of them, they are estimating the true Q function, which we denote as QA. Right? Both of them are trying to estimate the true Q function. So that means the expected value of this and the expected value of this should be an estimate of the true Q function, more or less. So the idea now behind double learning is as follows. So first, uh, when we think about this step number 2, when we take the argmax over all actions, right? So what we're now doing is saying a star, our optimal action, right, is equal to the argmax over all actions of Q1A, right? So we're using Q1 to estimate the argmax over all actions, right? So now that we're using Q1 to estimate the argmax over all actions, um, how do we now find the value of this action, right? So to find the value of this action, we are going to use, before to find the value of this action, we would still use Q1 if we look at the formula here because we're using the same Q function for both. But now in double Q learning, to estimate the value of A star, we're going to use Q2, right? So that means to estimate the value of this function, we're going to use Q2. So we're going to compute Q2 of A star, which is essentially equal to Q2 of the argmax over all actions of Q1A. Here I just substituted here into this. So this is what we end up computing now. So our update rule changes as follows, right? So how do we find the value of Q1 S comma A, right? This is the next question we also solve using this idea of double Q learning. So you need to pay attention a bit here. So if we take Q1 S comma A, we are going to compute it as Q1 S comma A plus alpha times the reward we get plus gamma, right? So again, so far we're following the same structure of this, right? But now, when we're taking the maximum over all of these actions, right? Instead of taking the maximum over all actions of Qs prime comma A, we are going to make use of Q2. So essentially, we're going to look at Q2, right, of S prime, comma, and then we're going to look at the argmax over all actions here of Q1 S prime, comma A, right, minus Q1 S comma A. So what happened here? What happened is now that, yes, when we're trying to find the optimal action before we're doing the maximum over the Q1 itself, we're still doing that. But to estimate the value of this action, we're using Q2. That's the difference here. So what double Q learning actually is we update Q1 using this formula, and to update Q2, we just use the same formula, except here we've got Q2, and where there's Q2 we have Q1. We just reverse Q1 and Q2. So what we do essentially is 50% of the time, like with a 50% probability, we'll update Q1. With another 50% probability, we'll update Q2. That's it. Like there's no other there's no other thing happening here. This is the entire magic of this algorithm. That we are using a different Q function to estimate the value of the optimal action determined by another, Q function. That's what double learning is in a nutshell. So since this is how we are updating things, the next thing we need to do, the next logical step here is to, shall I say, implement this double Q learning part. Okay, I am not gonna do it from scratch, of course, otherwise it will take forever, so I'm gonna copy our Q learning code. and we'll modify it from there, essentially. Okay. So the first thing we notice is we have two q functions, q1 s comma a, right? So I'm just gonna copy and paste this, and q2 s comma a. So q1 sa and q2 sa. That's the first thing we have. And in our research policy, again, oh right, I already copied this. Oh no, that's different. Okay, I'm going to say this is again q1 sa, q2 sa. Right, so that's all we do for the research policy part. And for the soft policies, now we defined q values here, but what we need are q1 values. Right, that's another thing. Like when we are actually determining what action we take using these two q functions, we just add the q values and take the maximum of those. This is essentially what we do. So when we're actually deciding on what policy to take, and by that I mean in the step of our algorithm, like when we are deciding should we take the argmax over actions of the q values. In the case of double q learning, we'll take essentially we'll take the argmax of q1 plus q2, right, when we're deciding how to act. So that part should be okay. So q1 values, q2 values is equals to an empty list. So yeah, you understand what I mean from the code, because we're just making the minimal modifications here. So again, this is just our epsilon greedy soft policy that decides what action we should take. So this part here, we're gonna say, I'm gonna copy paste this again. So we're gonna have q1 values, q1 s comma a, q2 values, q2 s comma a, and corresponding actions dot append. Okay, what happened here? Did I name it differently? Right, problem lies here. Okay, so that's what we do here. And what are the actual q values that we use to determine what action we're going to take? Well, to determine what action we're actually going to take, we're going to say q values is equals to np.array q1 values plus. So again, let me reiterate, for deciding what action we're going to take, we are going to add up the q values, the q1 values and the q2 values. But when we're updating our q1 and q2 values, we have this all 50% of the time we do this, the other 50% we switch the variables. So this is just the difference. So when deciding what action you want to take, just remember to add the q1 values and the q2 values, like what I did in our algorithm here. So as you see, everything else stays the same, except that like I just added this two separately. And then the final step is what I talked about before. So what we do here is we so I shouldn't call this q learning agent, but double q learning agent. So what we do here is we say, I guess this should be after possible q action, q values. Okay. So, right, now time to do what I was supposed to do earlier. If numpy dot random dot rand is greater than 0.5. So if this is greater than 0.5, this will be our update rule. Okay, so that's fine. Okay, so what are we doing here? So first we need to update the Q2 values, let's say, right, with the probability of this. So Q2 values will be equal to self dot Q2 SA, right? And in this case, I'm just going to return the action as well. I need to return this, and you understand why in a second. So I'm not just returning the Q2 values, I'm returning the Q2 values and the corresponding action. That's essentially what's happening. So for A in future actions, if it's in solve.q2sa, right? And now the maximum Q value, right? Now what is the maximum Q value equal to in our case? So what is maximum Q value? What am I computing? I'm computing this term now. I'm computing this term here. And if you look carefully, it's Q2 of S prime, comma, the argmax of Q1 S prime, comma A, right? So essentially, to compute this term, what I need to do is say, okay, we're going to say solve dot Q1 SA, right? So in our case, we're computing Q2, so this part would be Q1. And then what are we going to do? Q1 SA of S prime, right? S prime, this is corresponding to the S prime here. Now we need to compute the term here, the term in red here. I mean, we've defined this part, now we need to define the rest of this. And to do that, so we say S prime, comma, maximum, right, of Q2 values, right? And I'm saying 1. I'm saying 1 so that it actually gives me the argmax, the action. This is why I returned the action here. So this would be maximum of Q2 values and of the action there. And we're going to say, leave it like this, and we're going to say if length of Q2 values is greater than 0, else 0. So now to update Q2 of SA, it's solve Q2 SA S action solve alpha out self dot gamma max Q value solve Q2 S comma A. So is this okay? It looks fine, I think. If not, I'll check later after running it. But the next part where we say else, so with a 50% probability we update Q2, with another 50% probability we are updating, what do you call this, Q1. That means where there's Q2, I'm going to start putting Q1. This is Q1. This is Q1, maximum Q value. So this part becomes Q2. This part becomes Q1. This part becomes Q1. And this is updating Q1 S comma A. Q1. And finally Q1. I think. Should be fine. Maybe. Yeah, this is very messy code. I'm sorry for that. But I hope you get the well, the general idea, but I mean, this is the minimum. What you call this? Oh, this is what the, we just have to add some minimal changes from our original code, I guess. Um, okay, so double Q learning agent is equals to the double Q learning agent in our environment. So we initiated this. So left actions, I'm gonna call you agent 2 is double Q learning agent dot update policy, and I will plot you to here. So you are A2 and I will make you green and call you double Q learning. Okay. So here I'm just, well, if we have an error, then that's gonna be problematic because it's gonna, since I set it to 1,000 iterations, yep, here we are. So where did I make a mistake? Let's check. Somewhere, somehow, there's QS, A. If state A in self.qsa, this is where, right here, in line 77, no, in 33. Right. So, I can check it if it's in Q1 is comma A. These are pretty much the same, so should be fine. Let's see. Second time, so it probably means that it's doing something right, I'm guessing. And there we go. So now from this, you can already see the effect of double Q learning, because in this case, we have managed to actually, well, from the beginning, it knows now not to take the left actions more frequently before, and it converges faster, and it actually does converge uh, to the optimal, well, at least close enough to the optimal times that we should be taking the left action as opposed to Q learning. So just from this, this should motivate us to know how we can actually eliminate or minimize, rather, the maximization bias caused by Q learning when we implement double Q learning. So having said that, I think I'll end this terribly long lecture here. And next time, I think we'll start talking about bootstrapping. But yeah, let's see how that goes. So thank you kindly.